Hi, thanks for joining me. Today I'm going to be going over problem 1, part 1 from week 7 of the Summer Invariants Maths competition. As always, I'll leave the link in the description below with details of the competition. Anyway, this is the problem I'm going to be tackling today. We want to know, is there a non-trivial way to label the faces of a cube with positive real numbers such that each number is a product of its neighbours? Okay, so what we're going to do is we have a cube here and we're going to put numbers on each of the faces. So suppose I put A on this front-facing face here, and say B on this face to the left here, C on top here, D here, E on the bottom face, and then F on this back face. Okay, then every face is the product of its neighbours. So for example, A is equal to the product of its neighbours. Well, its neighbours are B, C, D, and E. So A is going to be equal to B, C, D, E. Okay, and so on. This property applies to each of the faces. Now we want to know, is there some non-trivial way to label the faces so with this property? And by non-trivial, I mean one which isn't just the trivial solution where each face has the number 1 on. Because obviously if I put 1 on each face, then it has this property, but that's kind of a boring solution. We want to know, are there any more interesting ones? Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to get stuck into a solution. Okay, so the answer is no. There is no non-trivial way to label the faces of the cube with the property that each face is the product of its neighbours. Okay, let me prove that. Okay, so let's look at face A to start off with. So remember, we have that A is going to be equal to B, C, D, E because it's the product of its neighbours. Okay, now what we're going to do is look at the opposite side of A, so that's F. So the opposite face is F, and well, F, remember, is also the product of its neighbours. Well, what are F's neighbours? Well, it's this face with B on it, this top face C, this face with D on it, and this bottom face with E on it. So we get that F is equal to B, C, D, E as well. But in particular, F is equal to A. Okay, so we get that A and F have the same number on. Okay, and that argument applies to any face you choose. Any face has the same number on it as its opposite face. Okay, so we can simplify this problem a little bit, and we can get rid of the F and put an A there. We can get rid of the D and put a B there, because its opposite side is this face here with a B. And we can get rid of the E and replace it with a C, because this face's opposite side is the top face C. Okay, now so we've got 3 sort of variables, and as I claim there's no non-trivial solution, we want to show that A equals B equals C equals 1. Okay, and to do that we're going to construct some simultaneous equations. Let's look at A, for example. A is the product of its neighbours. So that's B times C times B times C, which is B squared, C squared. Okay, similar thing for B. B is the product of its neighbours. Its neighbours are A at the back, this C on top, this A here, and this C on the bottom. So B is equal to A squared, C squared. And similarly, C is equal to A squared, B squared. Okay, and there are a few different ways we can solve this set of simultaneous equations. But the way I'm going to do it is do this equation divided by this equation. So I get C over B is equal to A squared B squared over A squared C squared. And I guess just one point to note is that everything is positive and real, so you don't have to worry about dividing by 0. Great, the A squareds cancel nicely. Let's cross multiply to give us that B cubed is equal to C cubed. And again, because everything is positive and real, I can just take the cube roots of both sides and conclude that B equals C. Okay, and if I compare these two equations in a similar way, do this one divided by this one, I'm going to get that A equals B, and thus A equals B equals C. And now the last step is to show that they're all equal to 1, and that's not too difficult. Let's just sub this into, say, this equation. So we get C is equal to A squared times B squared, but A and B are both C. So that's C squared times C squared, which is C to the 4. So that means that C cubed is equals to 1. And that, of course, means that C equals 1, and thus A equals B equals C equals 1. Okay, so we've shown that if there is a solution to this problem on the cube, i.e. if we have label the numbers such that each number is the product of its neighbours, then it must be the cube with 1 on each of its faces. Okay, that's problem solved, I guess. Join me in the next video where I'll answer the same problem, but instead of a cube, I'll be looking at an octahedron, and we'll see something special happens there. So I'll catch you in that one. Have a great day.